So this is our second organic reaction in chemistry. If you remember, last time we talked about substitution reaction of tert-butanol, and today we look at elimination reaction. So this elimination reaction is a reaction which we use to synthesize a double bond or a triple bond for that matter, and we call it elimination because during the process there is an atom or a group of atoms that removed from the structure. That's why the name elimination comes from. And these atoms or group of atoms that are eliminated are actually the leaving group and the group to be abstracted. So for elimination reaction to happen, to occur, we must have a group to be abstracted and a leaving group at alpha beta relationship with respect to the core carbon structures. So at the end of the reaction, you'll see a double bond or a pi bond formed, which is characteristics of this type of reaction. So this is general overview of reaction for elimination reaction, where we have a substrate and the substrate have a leaving group denoted by X and a hydrogen, which is the group to be abstracted. The leaving group is not always a halogen, as it is the same with the hydrogen. The leaving group might not always be also a hydrogen. But these reactions, substrate, alkyl halide substrates are most common substrates for substitution and elimination reactions, and we use them as an example in this overview. So there is this base, and when the base reacts with the substrate, we will have the double we have the double bond formed or an alkene formed and conjugate acid of the base. Depending on the nature how this double bond forms, as in the case of substitution reaction, depending on how the substitute product forms, we have also types of elimination reaction. So if the base abstracts the group to be abstracted, the hydrogen in this case, in the first process, and the leaving group. So when the base abstracts the hydrogen, because the base has a pair of electrons and it's abstracting the proton, not the hydrogen with electrons. So the bonding electrons will lie down to make the double bond, and the leaving group will leave due to electronic configuration fulfillment. So when the double bond is formed, this carbon, the beta carbon, will have 4 bonds, and as a result it pushes out the leaving group, and we have the alkene. So notice that here the base starts a reaction, which means the base and the substrate are involved in the reaction, and good evidence to say that this is a biomolecular elimination reaction or E2 reaction is by looking at the rate equation. So when you see the rate equation is proportional to concentration of the substrate and concentration of the base. Whereas in case of E1 reaction, there is no any base in the first step. Simply the substrate will proceed spontaneously into the carbocation as a result of the departure of the leaving group, and in the second step the base comes, abstracts the proton and makes the alkane, the final product alkene. So you see this is E1 reaction similar to SN1 reaction, because in the first step we see only one substrate, only one reagent going forward to form an intermediate. So the best evidence to see that this is E1 reaction is also to look at the rate, and the rate is equal to or proportional to only concentration of the substrate and is independent of concentration of the base. It's unimolecular because the rate contains concentration of one reagent. Practically, we'll be looking at synthesis of cyclohexene from cyclohexanol. This reaction is elimination reaction, and particularly it is acid catalyzed elimination reaction. So we will have cyclohexanol at the beginning as our substrate, and we will use the acid plus heat, and we will have cyclohexene and water as a byproduct formed. So the mechanism is simple. The acid protonates the OH group first, and then the OH group becomes OH2 plus and leaves the substrate, forming secondary carbocation behind. And then you can use the water, or you can use any abstracting group and abstract the proton, and finally the alkene is formed. It's a three-step process because it's E1 reaction. If you see the first step is similar to SN1 reaction, I mean we go protonation first. We make a protonation first, and then we go to carbocation formation. In fact, the first and second step are similar to SN1 reaction. However, this reaction goes through elimination reaction, but not through substitution reaction. And what do you think is that the cyclohexanol undergo elimination reaction, but substitution reaction? I may not give you the direct answer, but you can refer at the nature of the substrate and the nature of the leaving group. I mean the leaving group before it leaves, then what kind of leaving group is the OH itself, and you can get a clue to answer for this question. So in the actual procedure, we will take 25 milliliters of round bottom flask. Overall, we're going to do the distillation, so we will need a 25 milliliters of round bottom flask, and we add 5 milliliters of water into it, followed by 4 milliliters of concentrated sulfuric acid. And we swirl the round bottom flask to mix these two solvents. Please be careful here that when you do the swirling, don't do it with your hand, because when acid and water comes into contact, the mixture becomes hot, and and if you are swirling with your hand, you might not resist the heat of the bottom flask, so it will not be good for you as well for the experiment. And then I mean you're allowed to only swirl by grabbing the round bottom flask with a clamp, and as well because we said this mixture become hard, you need to cool the mixtures by putting the flask in, preferably in cold water, so that you can maintain the temperature of the mixture from 20 to 25 degrees Celsius. And then add 3 grams of the substrate, which is cyclohexanol in this case, and then add 3 boiling chips to the flask, because we are going to undergo heating. And then assemble the distillation setup as shown in the next slide. Here, your professor wants me to remind you that it turns out that there is an error in your textbook where the text refers to a distillation setup, but there is no the distillation setup that's required to be there in the textbook. So try to take the correction. Anyway, you just assemble your distillation setup like you see in the slide, where you have long bottom flask. This is all what should it look like, except of course the iron stands to support the setup, where you will have iron stand that supports the round bottom flask and the condenser, as well as the adapters. At least 3 iron stands may be needed, but this is how it should look like when the distillation setup is complete. So after you add your the sample, after you add the alcohol and the acid and the water into the round bottom flask and make the setup like this, make a gentle heating by turning on your heating source. If you are using a heating mantle, you just turn on the heating mantle and do the distillation for some time, particularly until you find the residue in the round bottom flask turning black and fume inside of the round bottom flask. And then you should expect to collect about 7 liters of your distillate, because the distillate, I forgot to show you that I forgot to show you, but so our sample holder is a test tube, and the test tube should be placed in an ice beaker to support a fast distillation of the distillates. And so in this distillate you should find about 3 milliliters of the distillate, and the distillate should be in 2 layers. Why? Because if you remember the reaction, we do not have only cyclohexene, but also we have water as a byproduct. And because cyclohexene and water are different polarity liquids, you'll see these 2 layers. And then using a Pasteur pipette, plastic Pasteur pipette or glass Pasteur pipette, you can remove this aqueous bottom layer from the test tube. And then add 1 milliliter of 10% sodium carbonate to neutralize trace acids, and do the washing with this solution by using this curling technique, and do that for about 12 squirts, just by drawing in and out the solution, and finally remove the sodium carbonate solution and proceed to the next step. And the next step is to again wash it with 1 milliliter tap water, and you can do the squirreling techniques the same way, just by drawing in and out the water, and after you do some skirting, you can then draw out and remove the lower aqueous layer, preferably the lower the aqueous layer is more denser than the organic layer, and you'll find it at the bottom, and you just remove the bottom layer. Once you remove the water, you have to add 0.5 grams of anhydrous calcium chloride. It will aid you in filtering the product, as well as drying out some unnecessary impurities in there, and then that's it. You're done. You can transfer your sample into a dry, clean, tasty tube, and that will be the product. However, if you see any emulsion in the product or any impurity, the best way to go for distillation again. In fact, we may not go to the distillation we have done before, but we can do this simple short pass distillation, as you can see in the slide, by transferring our the product liquid into the round bottom flask and heating it for some time, and then we can recover our pure distillate, just like you see, like you're looking at the slide. Things to remember: when you transfer the product, do not transfer the calcium chloride along with it. Just try to filter out only the cyclohexene. And also, when you make the distillation, try not to distillate it to the end, because if you distillate it to the end, the impurities will start to evaporate and again contaminate the product. And also, if you overheat, if you continue distilling, you may also lose your product because of the overheating. And then this experiment involves qualitative tests for the product, and the best qualitative tests for degree of unsaturation are the potassium permanganate and the bromine carbon tetrachloride test. If you add a sample alkene to a potassium permanganate, if the potassium permanganate is saturated, you will find a brome precipitate formed, or if you use an aqueous potassium permanganate, the purple color will disappear as a confirmation result of the experiment. Whereas using bromine molecule in carbon tetrachloride, you will see the disappearance of red or brown color of the bromine to colorless as a result of reaction with bromine. Detailed procedure for these qualitative tests are in your textbook, and we suggest you to refer your textbook. However, for your information, when you do the experiment, you should expect a color change like this: the brown color becoming colorless, or the purple color becoming colorless, as you can see in the test tip displayed on the slide. So the actual reaction is when we react bromine molecule in carbon tetrachloride with cyclohexene, a dibromocyclohexene, 1,2 dibromocyclohexane will be formed, whereas when we react it with potassium permanganate, an alcohol functional group having 2 hydroxy groups will be formed. Again, try to find the procedure for these qualitative tests in your textbook. And most importantly, safety matters, because you do remember that we have used sulfuric acid, and sulfuric acid is different from water, so we need to have a conscious mind in doing this experiment, because this acid is one of the most strong acids known, and it's known for its corrosivity. That's why we need to handle it with a great care. Adding water to acid is the wrong way of adding. If you remember the procedure, we add acid to water, not water to acid. If you do it the reverse, probably you'll find you'll find the reaction becomes extremely hot. You'll find vapors coming out, and you can also find bubbles for that matter. So that's not safe to do. That's not safe to carry on for the experiment. That's why you need to add water, acid to water, and not water to acid. Again, the process involves, when you add water and acid, you have to swirl so that the mixture will be effective, and in doing so the mixture is going to get hot, and if you try to swirl it with your hand, probably you're going to let the flask go and it will break, and again the acid will spoil in your foot or in your friend's foot, and that's not good. So the point is, try to hold the round bottom flask with a clamp or with a tongue, not with your hand, and do the swirling also by holding it with the tongue and with the tongue or with the clamp. So notice still that this acid causes chemical burns, and try to wash your hands if you feel any splashes in your hand, or in your hand, or in any body part, or it could be in your clothes. In fact, if you're opening this sulfuric acid container outside the fume hood, there is this gas that comes from the container, and it creates spills, droplets coming from the bottle, and they can splash in your clothes or in your hands. If they spill in your hands, you can feel them, and you should immediately wash them with fast running water. And again, in your eye, or any place around your eye, or in whatever place in your face, you have to immediately wash it with fast running water. However, if they are in your clothes, you might not know them during that time, but for sure, if you come in contact with any of those spills, you will find holes formed in your clothes when the clothes is washed. So try to be careful yourself not to expose to these acids or to their vapors also. Even cyclohexane, it might not be as strong as, it might not be an acid like that of sulfuric acid, but it is a volatile organic solvent. And you know what volatile means? It means that it's more susceptible to create a fire. And when you measure cyclohexane or when you transfer cyclohexane, you should be very careful not to trigger any fire hazards or not to go near any flames or any hot objects. Bromine itself is extremely hazardous reagent which can cause chemical burns as well as eye damage, and even it's extremely volatile which can cause respiratory upset. And always the TAMPS rule, the big rule in laboratory is try to do your experiment. Do your experiments in the fume hole. Okay. Again, potassium permanganate has a very interesting purple color. It's not also that acidic, but you should know that it's a powerful oxidizing agent which can cause chemical burns. If it comes in contact with your skin, it can also cause skin decolorization, and so you should handle all the chemicals with great care. That's the message here. Finally, with your product, try to measure the weight of your product, and you need that weight to calculate the percentage yield. Take the theoretical yield from the reaction given in the first slides, and you can measure the weight of your sample and calculate the mass using density formula, and then you can try also to record the temperature range at which the distillate comes out, and the distillate is expected to come out in between 77 to 83 degrees Celsius, and that also assures that you have got the pure product. Also, if you have the chance and time, try to measure IR and NMR to be more sure that your product is cyclohexene. And thank you for your time. Again, if you have any comment or question regarding this lab lecture, you can email me, you can write a comment in the YouTube channel, and yeah, thank you very much.